Now, probably one of my favorite methods in solving a system is called solving a system by addition, where what we're going to do is we're going to combine two equations to eliminate a variable. So some people might refer to the addition method or the elimination method. I call it the addition method because we're kind of adding or we're using two equations to eliminate a variable. So what does that mean, Willie? You just said a lot of words there, but I need to see some action. Okay, what we're going to do is we're going to try to add these equations with the hope a variable gets eliminated. So what happens if I just add vertically? X plus x produces a 2x. Y plus a negative y disappears. 4 plus 6 equals a 10. Now I have a 1 by 1 equation, or 1 by 1 system. One equation with one unknown. Now let's solve that. Divide both sides by 2. X equals 5. So we're halfway there. Let's take that 5 and plug it into our original system into either one of those equations and solve for the other variable. So if x equals 5, so if I use the x plus y equals 4, x equals 5, solve for y equals negative 1. So the solution to my system, not x, is 5, negative 1. And we can check that to find out, is 5 plus negative 1 equal 4? 5 minus a negative 1 equal a 6? That is true. So the solution is 5 and negative 1. Okay, you guys are going, wait a minute here. I think I like it, but I'm not sure. Can we see some more examples? All right. All right. So a little bit of a strategy here in solving a system by addition. First thing is, let's make sure that we can write the system in standard form so that the variables line up on top of each other vertically. 3x minus y lines up on top of 2x plus 5y, and they both equal a constant. From there, we want to see if we can add them such that a variable is eliminated. But right now, if I add them, a variable isn't eliminated. So what do we do? What do you think? I bet you that if I multiply, I think I heard somebody say that, if I multiply the top line or the top equation, both sides by a 5, I'm just going to put a 5 right there, which is a little bit of a memory for me. I'm going to multiply I'm going to multiply 5 to both sides. And we can do that because whatever we do to one side of the equation, as long as I do it to the other, it's completely valid. So let's do that. Let's rewrite this system in. So this becomes 5 times 3x minus y equals 11 times 5. Solve that down a little bit. That becomes 15x minus 5y equals 55. All right, I like that. So let's use that then. That's equivalent to my first equation. Let's take the second equation, which we did not modify. There's my system. Those are my two lines. These two lines are still equivalent to in the first system. Now we can add them. And when we do that, a variable is eliminated. 17x plus 0y equals 68. And then divide both sides by 17. Looks like x equals a 4. Cool. That seemed fairly straightforward. All right, so what do we do now? Now we back substitute, which means we take this value and we back it up to one of our systems, one of our 2x2 systems, and solve for the other variable. And let's do it in the first one. So 3x minus y equals 11. 3 times x, which is now 4, minus y equals 11. And I have the solution, not x again, of 4, 1. So this system has a solution. We're going to call that a consistent system, meaning that there's a solution there. And I have the solution of 4, 1. All right. So what are you guys thinking about this particular equation or this particular system? What do you want to eliminate? Do you want to eliminate the x's or the y's? Doesn't matter, whatever your choice is. However, in this one, I think I'm going to do something that we'll see sometimes to just show you that sometimes we might need to multiply by a negative value as well. So let's eliminate the x's. So I'm going to multiply the negative 3, or that's going to be my multiplier to both sides of the equation. Basically, it's called a scalar. So I'm going to scale both of them by a negative 3. This becomes a negative 9x minus a 6y. And negative 3 times 48 is 100, 150 minus 6, 144. My second line remains unchanged. So now I've modified my system. It's still a 2 by 2, meaning there's 2 equations and 2 unknowns. And my goal is to get it to a 1 by 1. The x's eliminate in this one, so I have a negative 14y equals minus 168. And then divide both sides by negative 14. Y equals 12. And then from here, we back substitute. So we take that value, plug it into our system, whatever equation you feel like might be the easiest one to do. 3x minus 2 times y, which is a 12, equals a 48. So 3x minus 24 equals 48. Add, okay, I want to make sure 3x, oh, that's a plus a 2y there, isn't it? Plus 2y, plus, good thing I caught that. Didn't want to solve the problem correctly using a bad value. Subtract 24 from both sides. And now I have my two values. 8, my x coordinate is 8, my y coordinate is a 12. And so the solution to this system is the coordinate 8 and 12. Now this one's kind of fun, but do you see what we're starting with? Yeah, that's right. In order to solve a system by addition, and we want to eliminate a value or a variable, we need to make sure both lines or both equations are in standard form. Aha, not here. So let's rewrite the system. And then you can verify, basically I subtracted 7y from both sides. Here, I added 3x to both sides, and now I have an equivalent system, but written in standard form. However, though, if I multiply one line by a scalar, nothing's going to drop out. Oh, maybe this is the example or a time where we have to do something to both. So if we wanted to eliminate the x's, I need to kind of get both a 2 and a 3 to go into the same number. And I think if I can get it both be 6, but opposite signs, they would drop out. So let's multiply the top one by a negative 3 and multiply the bottom line by a 2. All right, or scale the top one by a negative 3. So negative 3 times 2x gives me a negative 6x, a plus a 21y, equals 17 times 3 is 51. Negative 3 times 2x, positive, positive. Bottom line, I'm going to scale it by a 2, or a factor of 2, so this becomes a 6x plus a 10y equals a 34. Now notice I still have 2 by 2 systems. The first attempt was to rewrite them standard form. The second part was to work in some type of way that I could see a variable to eliminate. And now I do. The x's can eliminate, which makes a 31y equals an 85. All right. I'm just checking these numbers here, see if I made a mistake somewhere. I just got some nasty numbers. I even write the problem down right. How many of you guys have ever solved the problem in that right way? Nope, must be what we have. So y then equals 85 31st. A little ugly there. I was hoping it would be a little bit better, and I can't find a number that eliminates out of that. So what do we do next? Well, we take this value of y and plug it into one of those systems and solve for x. Or I can start from the system all over again and eliminate the y's. Let's try that. Let's go back to this system right here. Yeah, that's clever if we did this. These two systems are the same point right there. So this time, let's have the y's eliminate. So let's multiply the top one by what? A 5. And scale the bottom one by a 7. So 10x minus 35y equals a negative 5 times 17, 35, 85. Did I do that right? 5 times 5, 35, 3, 85. Multiply or scale the bottom one by 7, 21x plus 35y. That's what we were hoping for. 17 times 7, 119. Y's cancel, so I have 31x equals 119 minus 85, 15 plus 19, 30, 34. Solve for x. X equals 34 31st. Those are my two solutions. So my coordinate point is the point 34 31st and 85 31st. Whew. Yeah, it would have been a lot of work to back substitute into the equation to get the other one. Would have been a lot of work to do it by substitution. Would have been a lot of work to get that precise graphically. So good thing I was able to use the addition method here. The method works even though I got a number that's a real life number, just not a clean number. But it's still the answer to our system here. So that was a little bit of a clever move you guys decided to do. Solve the system twice by eliminating first the x's and then do it again by eliminating the y's.